Yeah, hello everyone. Today we are talking about not only a random forest, but about ensembling in general. I've been working on this topic for the past 3.5-ish years. So I give you a little insight on how you can use ensembling for, or why you should use ensembling for various reasons. Um, First of all, the main reason why we start with decision trees is because lots of ensembles are used on tree-based models. And we first start with a very brief overview of decision trees in general, before we then continue to the main topic of today, ensembles. So let's start with this little example. So these are data points in the plot. The red circles represent medium salary jobs, or not jobs, but yeah, medium salary jobs, and the green crosses represent high salary jobs. On the x-axis, you have the average marks, and on the y-axis, you have the study time. So here you can basically see how much students have studied, what the average mark was, and then in the end, if they got a medium or high salary job. Good for you. No low salary jobs are seen in this plot, so a bright future ahead for computer science students. But if you would need to classify this plot in general, and you have a random new data point that appears, can you see any kind of rule that could help you classify them as a high or medium salary job? Yeah? Yeah. Yeah. So basically what you're saying is if your mark is basically between 1.0 and 2.0, and your study time is below 30 hours per week, you have a high chance to get a high salary job. And that's exactly what decision trees do in general. They find these rules to split the data space into multiple parts to easily classify data points. So for example, this data point that now appeared in the top half of the plot is an unknown. Let's assume it's an unknown data point, but we already know it's a high salary job. And if we would like to classify it, we could basically divide the data points into these two groups. So you have students above, let's say, 2.5 in an average mark, and they most typically get a medium salary job, and everyone who has a better grade than 2.5 in general gets a higher salary job. And that's already a very easy classifier, let's say. If we want to be more precise, we can enable more rules. So for example, if we have this second line separating the data points, you can see that our accuracy will probably even go higher. Because here we are in the upper right corner, we basically only have low, medium salary jobs. The pluses were the high salary ones. So the medium salary jobs. So you know that in theory, based on this data, if you have a grade above 2.5 and you studied a lot for it, then you will get a medium salary job. And as I already said, this is the basic idea of a decision tree. A decision tree is a tree-like structure. I guess all of you have already heard algorithms and data types. So you have a basic idea on how a tree structure looks like. In decision trees, these they don't have a defined depth of the tree, but every root node can have two branches to two further nodes. So you can't have three or multiple. So that's the first very general rule. And then with this tree-like structure, you can basically, I think I need to use the cursor, otherwise the online people can't follow. You can basically say that with these two steps, you can clearly distinguish how a data point looks like. And I mean, until this point, this is really simple. It's basically just rule-based. We introduce two rules, and based on how you answer these two rules, you basically know what data point it is. This is a big advantage of decision trees because they are very easy to follow. They're super simple. I mean, you don't need to study computer science and especially not machine learning to understand how to split up data points by rules. And then it's very explainable as well. So in machine learning, we often have the issue that the outcome or why we classify an item in a certain way is pretty hard to explain, because if you have linear regression, you have a learning rate, you make gradient descent, and in the end, you end up with a linear representation of the data points. And I mean, most people can't follow from that point on. With decision trees, they basically can. So let's recap the basic idea and the advantages of it. So it's basically just if-else clauses in a tree-like structure. The nodes verify or evaluate the features, the branches embody the feature values, leaves classify the instances. Decision trees are kind of old. They come from expert 60 systems that were introduced in the 60s and 70s. And no, this is also very important. Nodes of the same level are not connected. So this is not a graph. It's a tree. They can be used for classification and regression, even though they are not well suited for regression tasks. So decision trees are typically used for classification. In the 70s, I mean, today we construct these trees automatically with software. In the 60s and 70s-ish, they did it by hand. So they looked at the data points and they came up with rules, and based on these rules, they construct decision tree, and then depending on how complex the data was, they had better or less performance. Let's do one last example before we switch to ensembles. What would you think? These are supposed to be cakes, very abstract cakes, full cakes and slices of cakes. But the question is, in the end, if Johnny likes the specific cake that is seen at the very bottom. What is your guess? Would you say that he likes the cake or he doesn't like the cake? Yeah? He will like it. Why? So what are the similarities? The filling is dark, yes? It's a circle shape. Okay, yeah. So the outer crust is thinner, it's a circular shape, and the filling is black. Yeah, and that's pretty much what we would come up with. I mean, typically you don't only have an image, but you have data. So you have a data table, and then you can construct the exact same. So this would be a very good example. And again, it's the shape equals circle. Yes, the filling is dark. Yes, so all cakes on the left side that have a dark filling and are circular shape are the ones that Johnny likes. So this would be, for example, one way of building up a decision tree to find out if Johnny doesn't like the cake. So for example, if the filling would be white, he would most likely doesn't like it because here many of the fillings are white. Or if they are shaped in a square-like structure, then there are also more representatives on the don't like side. That you can rather say whether he would like a cake with specific attributes. So you can also do this for multi-label classification, because when you split up the data space, there can be more classes represented in there, not just two. Until now, we just classified binary classes, but there can be multiple. As you can see in this very easy example shown on the slides. And this is another, let's say, I wouldn't necessarily say advantage at any point, but if you introduce a new data point, for example, this shape data point in the upper right corner of the plot, I mean, this would most likely be misclassified, right? And it's in this example, it's very easy to see. But what you can always do in decision trees, you can just add multiple rules to split it in different ways to include it to the right data points. And then you can decide whether you accept a certain degree of error or you adapt and incorporate multiple new rules to actually shape the decision tree. But you have to be careful. The more rules you employ, the more complex the decision tree gets. So we already covered some of the advantages. First of all, the decision trees are pretty effective for simple data, but they can be also very, very effective for complex data. But then we need an ensemble of them. They are very easy to understand and explain even to non-computer scientists. They are mathematically less demanding. Like you don't have to learn vector spaces, you don't have to build embeddings. There's no deep learning involved. It's pretty straightforward. It's simple. You don't need to pre-process the features because it typically can adapt to all kinds of features. That's if you want to use linear regression or other kind of classifiers. For some of them, pre-processing of features can be pretty important to get meaningful results. A very nice thing with them is they work on little data. Like today, especially in the medical domain, it's very hard to use machine learning because typically hospitals, they don't really share their data. And it's also legally very challenging to share medical data. So most of the hospitals or medical groups only have few data points. And most machine learning algorithms, they really start to shine when they have like millions of data points. But this is for a domain like medicine is not really possible. So decision trees can really train well on small data spaces because it all depends on the rules and not on the amount of data points that you have. So they can cope with outliers quite well, and they're pretty fast. Computer doesn't need long to answer 2 rules for a decision tree. Disadvantages are new data points can change the tree significantly. So we had this example with this red circle where we had to adapt the rules in the multi-label classification. So when you do that, you have to reshape the whole tree. So it's not just that you add a new leaf node or new branch to a specific node, but you have to reconstruct the whole tree. And depending on how often your data changes over time, this can be pretty painful. They are not perfectly suited for regression. And normal decision trees are not suitable for large data sets, especially complex data sets, because, I mean, all the examples that we had here on the board, you could basically pretty much see certain boundaries in the data. If you have very complex data, then you typically can't see the boundaries. So then decision trees usually don't perform as well. This is one or the last example of decision trees. This is the IRIS dataset. It's a pretty common dataset when you start with machine learning. You probably have used it before in one of the labs. I'm not sure how the labs look like today, but in the past, there was 1 or 2 examples where you use this specific dataset. And you can basically achieve almost 100% accuracy with decision trees because the space, if you map it to a 2D space, you can pretty clearly see boundaries that you can set for decision trees. So this is a very good example on a benchmark dataset where decision trees really can shine because the boundaries are pretty distinct. Yeah, so Professor Behl made these slides, and he also included lots of more videos that you could watch in your free time if you are very interested in decision trees. I know that this was so far really brief, so we haven't really talked about how to build your own decision tree rather automatically. More use cases on decision trees and how to use them for more complex data. Because, and this is a little spoiler, I guess until pretty much a year ago, decision trees or models that are based on decision trees were still state of the art in tabular data. So all that we are doing in machine learning is we work on tabular data. Tabular data is all the data that you can represent in a basic table. And all the data sets that we use in our labs are typically pandas data frames. So they are not graph data and they are not some form of image data or whatever. It's all tabular data, and it used to be state of the art to basically rely on decision trees. It gets more complex. We get there in a second, but the concept is still pretty simple. So let's switch to the next slides. So from now on, we talk about ensembles and what they are and what they do. We get there in a second, but we first start with a little example to, wake you up a little and maybe show the core concepts very easily. So let's assume the intelligent systems group has a soccer team. And the blue player is of course the ISG player, and he gets fouled in a duel, and well, his knee cracks. So what you typically do in these kind of scenarios, you visit a doctor, and because he's very afraid that he will probably no longer be able to play in the league, he visits a knee specialist and looks at the knee and basically says it's fine. So, but still, he heard the crack, and he's very unsure. So if you, let's imagine you're the soccer player, Bob, and the knee specialist tells you, well, your knee is fine, you don't really need to worry. But you're very unsure and you heard the crack. What would you do? Yeah, you would go to another doctor because you wouldn't rely on just one opinion, right? So then he attends multiple doctors. And can we hide that? And he attends 5 in total. And 4 of them say, well, that's definitely a knee injury. And one of them tells you your knee is fine. So what would you conclude? Yeah. That's not a silly question. We come to that in a second. But what is your conclusion on the data that you have currently? Would you say it's a knee injury, or isn't it one? Yeah. Yeah. So you said the majority says it is. So you're doing majority voting. So in the end, how you could see this is every doctor represents a classifier, and it classifies your knee as either injured or not injured. And if you're not really, if you don't trust one single classifier, you just take multiple. And then you look at all their output, and then in the end, you can do a majority vote. In this case, 4 out of 5 say it's a knee injury. So you could be pretty certain that in fact it's a knee injury. But now your stupid question comes in. What happens if I tell you the profession of the doctors? Like the one that he visited before and said the knee is fine is a knee specialist, but a heart surgeon, a vet, a dentist, and a cosmetic surgery basically say your knee is fine. Would this actually change your decision? Yeah. Yeah. Okay. Okay. Okay, yeah, and I'm in the end, I'm not really sure what is right or wrong because I'm not Bob, it's not my knee, and I don't really care. But the interesting part is you said you put a weight. So if we get back to seeing these doctors as classifiers, based on their profession, you can put a weight on it. So you trust one doctor more than another. So in this case, it could be that even though 4 out of 5 doctors say it's a knee injury, you could still believe it's not one, because the one that is really specialized on your specific classification task says, well, it's fine. Yeah. So you could weight these doctors. And as you say, me personally, I wouldn't go to a vet to analyze my knee, but there is a somewhat chance that even a vet can see if a knee is swollen and under pain and whatever. But in general, this is basically what we are doing in ensembling. So instead of relying on a single model, we rely on multiple. And sometimes we perform the classification with multiple models and we do majority voting. But in other scenarios, we basically want to weight them. For example, if we have validation data and we know on the validation data, one model performs a lot better than all of the others, then typically you want to give this specific model that performs great a higher weight than all the other models. And then you can build your ensemble. And in the end, the goal is to improve the performance. In this case, to be more sure if you really are hurt in your knee or not. But we typically in computer science don't visit doctors, so we have data, yeah. And we work with data. I mean, in an ideal scenario, we don't visit doctors that often, yeah, but work with data more often. You see where I'm getting. So throughout the rest of this lecture, we stick to our first example, and we always work with this rather small data set of 7 data points. And we have the features, age, swollen, pain, movement possible, and in the end, our label, whether the knee is really injured or not. And we could discuss a long time, or for a long time, whether the age is really a good indicator if your knee is injured or not. But this is the data that we have, and this is a typical machine learning task. You can't just construct the data that you think is perfect, but you have to work with the data that you get. And this is the data that we are getting, and this is the data that we work with. So maybe to reduce the chance that there is a single student in here that couldn't get the example. We do it again. So we have a model. The accuracy is 52%. And this really makes our ISG student unhappy because 50% is not enough. We want 100% accuracy. So we train more models. We ensemble them. We improve the performance to almost 100%. And this is happy. That's what we are here for. Okay, let's have a very abstract way of seeing an ensemble model. So you have input models, and what kind of models have you got to know in this lecture before? And linear regression is one of them, right? What is another model that we've learned? Yeah. Nearest neighbors, yes. Yeah. Clustering models, yeah. Yeah. And the interesting part about an ensemble is, so these 3 models could be all KNN models, yeah, that have different hyperparameter settings that are, yeah, slightly different, and you could use them in an ensemble. But what you also could use is you could use linear regression, the clustering one, and KNN as 3 models, and then so they all focus on different aspects of the data. So maybe that's a more diverse set of ensembles, right? There are a million ways. You could also include models that are trained on different kind of data. Like in some scenarios, you have different data sets that all play a crucial role in one prediction task. So you could train them on different data sets, different distinct data sets, and still ensemble them to improve the performance and take multiple facets into account. And then what we also have, we have inputs to the ensemble model. So we have certain, let's say, hyperparameters. It's how many models do we take into account? Do we weight those, or are we performing majority voting of the models? How are we actually aggregating their predictions? And so on. So there are multiple hyperparameters, multiple decisions that we have to take. And in the end, we are getting our predictions. And in ideal scenario, the quality of the predictions is a lot higher than compared to a single model. Generally speaking, we decide to between 2 different types of ensembles. So you have sequential methods and you have parallel methods. So sequential methods are basically you learn the model sequentially. So the performance or the output of the first model that you have trained impacts how you train the next model. Yeah, and then you continue like this. And typically you also have a learning curve. And if the learning curve looks the way you want to have it, or you try to target a specific number, whatever, what your criterion is to stop, you can stick to the ensemble and use it. So the parallel method is what I used as an example before, right? So maybe that's a good way of saying it. If we remember our example with the doctors, like typically, if you would trust the first two doctors fully, and they both agree on whether it is an injury or not, you would probably stop attending doctors, right? Because I mean, there's a sequence to it, depending on how the doctor performs, like his impression, his explanation, his in the end, classification will affect on how long you will continue to attend doctors until you are really sure whether it's a knee injury or not. The parallel method is, for example, when we use a KNN algorithm, a linear regression, and a clustering algorithm. We can train them all in parallel. Like if you have a CPU with 64 cores and you just need a single core to train linear regression, then you could train 64 models at the same time and then use them all. So these are the two differences. So in parallel, the base learners are really independent, and they always have the same goal to get better scores. So ensembling in general combines individual models to improve the quality of predictions. They combine the results of individual models to produce final decisions, and the final accuracy of combined models is better than the result of a single individual model. I mean, these are the three main takeaways. Okay, let's start with bagging. Bagging is one ensembling technique. And from now on, the lecture will be like really hands-on, not many formulas, pretty straightforward on how it works. I don't know whether you like it, but hopefully more people can follow and understand it. And it's important to know at this point that bagging is used in the classifier random forest. Yeah. So bagging and random forest are two different things. Like random forest is a specific model that uses bagging. Bagging is the general concept that can be used in multiple models. So the idea of bagging is basically you have the original training data and you split it up in bags. So out of this one data set, you create n multiple resamples. How they look like, we're going to get into that a little later. And then you train all these models just on a bag, not on the full data. So what could be the reason to just train them on the bag and not on the overall data? Yeah. Yeah. So that's exactly why we do this, because if we build an ensemble of exactly the same model, they can't contribute because they all agree on the classification in the beginning. Like there is no need to train 10 times the exact same model. So you want to have differences in your models. And ideally, they focus on different aspects of the data. So if you just have a single data set, you just split it into multiple bags, and then all these bags have slight differences. And then you train your model on these different data sets. And in the end, hopefully they focus on all on little unique parts of the data, and then the aggregation is a lot better than just training it on the overall data set. And in random forest, I mean, here we have the green classifier models down there, and these can be anything again. And I mean, this is how bagging works. Yeah, you subtract your data set into bags. And now we come to random forest. And in random forest, we use bagging, but the single classifiers are all random or decision trees. And the author of Random Forest was really creative, because if you have multiple trees, you end up with a forest. So therefore, a forest consists of trees. Great. Okay. So the first step is we want to create these bags. And in the following example, we just create one bag. And how are we doing it? We basically the bag should be the same length as the original data set. And then we sample randomly. So in this case, we start with 3, then we render, we sample data point 6, and then 4, and then it's 3 again, because we can sample a data point multiple times. And in the end, we have a bag. So what would you say? How much percentage ends up on average in a bag of the original data set? Because obviously you will end up with duplicates. Random guess. There is no right or wrong. Yeah. Or half, yeah. Good guess. Yeah. 68, yeah, that's 66% is on average what you would achieve. So basically you lose 30% of your data per bag. And the interesting part is every bag loses another 30%. Yeah. I mean, there is a chance in theory 2 bags could end up with the exact same data points, but depending on the length of the data, it's a slim chance. And then we want to build a decision tree. And this decision tree, not as in the decision tree example where we classified cakes, we want to know whether it's a knee injury or not. So in a second step, and this is then unique to random forest, or it's basically a hyperparameter, but we set it to 2. So when you train a random forest, to even more differentiate single models from each other, to make them even more different, we only focus on a subset of features. So in our case, this is set to 2. I don't know what the default value of scikit-learn is, but you could easily look it up, how many features per bag to take into account. But this is just another step to really make them more diverse. So in our case, they're randomly picked, and we randomly picked age and pain as the 2 indicators whether it is a knee injury or not. And then we want to build a decision tree. We haven't built a decision tree yet. But yeah, maybe it's interesting. How would you start? When you have the data and you know, okay, these are the data points, I want to focus on age and pain, and in the end, I want to build a decision tree. How would a good decision tree look like, in your opinion? How would you start? Any ideas? Yeah? Yeah? Okay. So first of all, building or constructing the tree based on binary information is a lot easier, because you can have for the pain column, yes and no, these are the 2 branches. Yeah, pretty straightforward. It's a lot more complex for the age, because you could say it's above 28 or above 35 or above 44, like who knows. Yeah. What? Yeah. Yeah, the decision trees are always binary. I mean, this is how they are defined. I didn't come up with the idea of decision trees. I mean, I wasn't even born when they were working on decision trees, but they decided they have to be binary. I'm quite sure there are examples where they use multiple nodes, but in general, in the core concept, they are binary. But I guess you were on the right track. So in the end, to me, it would really matter on which feature is more capable of splitting the data in half. Like if we remember the data space that we plotted in the decision tree slides, you could clearly see like there's a cutoff point. And typically one feature is better than cutting the data in half than the other feature. And then you want to stick to that. But if we just have the data, it's not easy to see, and it's not feasible to plot the data every time and then let a human come in, or someone that works on visual computing build a whole nother model just to see how the data could be split. So what we are doing, we use the GINI index, or the GINI impurity. And this index basically tells us on how good a certain feature is to split the classes in half. And we start with the more complex example, with the age example, because it's, as I already said, it's harder for numbers to come up with a threshold than for binary information. And I assume that you're a lot more awake in the first part of the lecture. So we start with the harder one. So what we typically do is between those data points, we insert these red numbers, and these red numbers are all possible cutoff values that make sense. So typically the red numbers, where's my cursor? It's the average between those two numbers. So 10 and 10 doesn't really make sense, but then 19 splits 28 and 10 apart. Yeah. So if you said more or less than 19, you know that the cutoff point would be here. And it's impossible. It's important to know. I mean, I was a little too fast. I skipped one step. You first order the data points by age, right? Otherwise, these intermediate steps, they wouldn't make sense. You order them first, and then you insert these intermediate steps, and then you have all possible cutoff values that could work for your tree. And then this is now very visualized, and the computer can do this a lot faster, but you actually try to analyze on how good the specific value is to split the data apart and how pure or impure the outcome would be. So typically we do this with a little decision tree. So the first threshold is 10. It's the first red number. Yeah, it's the first red number. And then you say, okay, the age is either smaller than 10 or larger than 10. So in case smaller than 10, there is no data point that is smaller than 10. So the left part of the tree is filled up kind of easily. And the right part of all the data points that are larger, where the age feature is larger than 10, 4 of them say it is a knee injury, and 3 of them say it's not. And then we have to calculate first the GINI impurity for both leaf nodes, and the formula is down here. So the GINI impurity is 1 minus the probability of yes, so the probability of this case, squared minus the probability of this case squared. So if we just paste in the numbers for this specific node, it's 1 minus 4 divided by 7, because overall this leaf node has 7 data points, squared minus 3 divided by 7, because again, the leaf node includes 7 data points. And then you basically just type it into your calculator and you come out with a GINI impurity of 0.49. You do the same for the left-hand side, and it's pretty easy because it's 1. It can't really decide on anything. And then you calculate the total GINI impurity, because both leaf nodes should get a different weight. So you basically multiply the number of nodes, or the how do you say it? You take the fraction of data points that are represented in either of the nodes and multiply it by the impurity. So in this case, here are no out of 7 data points. So 0 out of 7 times the impurity of 1, plus 7 out of 7 times the 0.49, and you end up with 0.49 as your final total score for the threshold of age smaller than 10. Yeah. These seem like a lot of steps, but actually it's the exact same step. And once you implement it, it's straightforward and it's somewhat fast. So then we continue with the second threshold, and in our case, this is 19. And again, the left leaf node is when smaller 19 is true. And we basically have 2 data points where this is the case. And both of the data points say it's no knee injury. And then on the right-hand side, these are all the data points that are actually larger than 19. And here, 4 say yes, and 1 data point says no. And then we paste it into the exact same formula again. So first we calculate the GINI impurity, Two data points are represented in this leaf node. So the probability of yes is 0 over 2 squared minus 2 over 2 squared. So it's 0 because this leaf node is actually really good in separating the data. Yeah. And this one is less good in separating the data because it's unsure on this data point, but we come to this later. And the total GINI impurity is 0.29. And then you do this for all the intermediate steps. So for all the possible thresholds. And in our case, these are all the GINI impurities that we end up with. And the lower the GINI impurity is, the better the threshold is capable of splitting the data apart. So in our case, there are two possible thresholds that work equally well. So we could either say it's 19 or it's 28. So the age is smaller than 19 or the age is smaller than 28. But yeah, this is the optimal GINI impurity for the age group. Now, to decide which of the questions comes first, so whether I ask first about the age or first about the pain, we also have to calculate the GINI impurity for pain. And this is a lot easier because you don't have all these intermediate thresholds, but you basically have true or false. So in this case, it's just pain. And when pain says it's yes, so these are all those data points down here, then 4 of them say it's a knee injury and 1 say it's not. So to translate this to meta level, it's basically if you have pain, in 4 out of 5 cases, you have a knee injury. In 1 out of 5 cases, it's painful, but it's not actually an injury that needs to be treated. And then here, if you don't have pain, well, both of the patients, they didn't have a knee injury. And then you calculate the GINI impurity as before, and the total GINI impurity is 0.23. Therefore, pain comes first, because if we split the data apart by pain, we have a lower impurity. So it's better suited to split the data. And this is actually then how the decision tree looks like. Because if we say pain equals no, there's only one outcome. There is no second question. If you don't have pain, you don't have a knee injury. And the second question is, if your age is smaller than 19, you probably don't have a knee injury because you still have the young bones. And probably everything is a bit more flexible and not that prone to injury. And if you're older than 19, there is a high chance that you have an injury. So this is the decision tree that we come up with based on our 2 features and our GINI impurity thresholds and so on. But we actually don't know how good this performs, right? So based on the data points and the features, this is, in this simple way of building a decision tree, the best that we can do. But we don't really know how good it performs. So before we come to how good the single tree performs, we, in decision trees or in random forests where we rely on multiple decision trees, we build hundreds of them because this is very cheap. Building a decision tree won't take you a second. Yeah, a lot less than a second. So you can build them fast. And trick question, is this a sequential or a parallel method? Yeah. This is a parallel method because the outcome of one tree doesn't really impact all other trees. So you could build all of them in parallel. If you have 64 cores, you could easily build 64 trees at the same time. So building 100 trees is a matter of milliseconds. What? What do you mean by pairs? Do you mean the pairs in terms of the features? Yeah, randomly. Every bag and every tree has a random number of features that you pick. So all trees are trained on a different set of features. This is a hyperparameter of random forest. Oh, they can. I mean, it's random. In theory, they can, but typically they don't. And then you make the trees more different so that they can contribute to the ensemble a bit more. Yeah. Okay. So in the end, now we ended up with 6, but in the real world, I again guess the default value of scikit-learn is 200-ish trees by default to train a random forest. And I mean, with the toy data sets of scikit-learn, you can train a random forest quite easily on your local machine. It's also in the labs. I don't organize these labs anymore, so I don't know precisely what is in there. But when I did a while back, there was one example where you actually trained your random forest locally, and then you can play around. It's an easy hyperparameter. Try to increase it, try to decrease it. You will see that in most cases, if you increase the number of trees slightly, the performance will go slightly up until a certain point. I mean, at one point, it doesn't make sense to add more trees because you already have a good representation. Yeah, but in the end, we need to find out how good our tree works. And we have validation data. Why do we have validation data? When did we make the validation split? Yeah. You could use a different bag, but then there is a chance of data leakage. Yeah. Right. We said that we typically end up with 66% of the data points in a bag when we randomly sample them from the data set. So that leaves us with around 33% of the data points that are not in the bag where we can actually evaluate the performance. And how do we predict with our random forest? It's also pretty straightforward. You basically answer these questions. So if we look at our first tree, large enough, yeah. So this data point says the patient has pain, yeah, and it's actually not smaller than 19. So this tree would actually say it's a knee injury. Well, we now include another tree in our random forest that say it's not a knee injury. And a third one says it's a knee injury again. And now we are at the same stage as we were in the very beginning with all these doctors that had their opinions, and we need to aggregate them into a final decision. The exact difference is the following. Like the test data is the split of the data that you use for the prediction or evaluation at the very end. Like typically when you work in a machine learning scenario, the first thing you do is you make a test set. Yeah. And then you put this aside and you will never ever touch it again until you do your final evaluation. Like the validation data used to be part of the training data, right? So this is a secondary split. And in our scenario, I mean, now what we could do here is we just majority vote. Yeah. So we majority vote and say 2 say yes, 1 says no. So the majority says yes, and we classify the data point as a knee injury. But we have the validation data. So if you remember the example of the doctors, we had their specialization included in there, and you could give them weights. So what we could do at this stage is we could use the validation data to evaluate the performance of each and every tree. And if we see that on the validation data, specific trees perform like really well and others don't, you could give them more weight in the final decision. So you can use the data to evaluate the performance, but you have to be careful. This is not the final performance of your model, because this is always captured on the test data that you put aside at the very beginning. So the validation data is always there to optimize your model. Like you can use it for hyperparameter optimization. You have the same issue. If you use linear regression and you have your learning rate alpha, multiple learning rate can lead to multiple performance outcomes. And you can use the validation data to decide which hyperparameter works best. And then if you decided on the best possible model, you can evaluate it on the test data. But there is no guarantee based on how you split the data. If the validation set does not represent the test set, you could optimize on something useless. But typically what you try to achieve when you split the data, that in general, the data distribution in all of these test sets somewhat looks similar. So that when you optimize on the validation set, that you also improve the performance on the test set. Welcome. Okay, so in this case, let's get back to this example. We do just majority voting. We don't use validation information. So the majority says it's yes. So therefore, we say it yes. And here you have to be careful again. Bagging, random forest and bagging are two different things. Like we now explored how random forests work. Yeah. And random forest, the implementation by default uses bagging. So the bagging is the process of bootstrapping the data. So creating these bags by randomly sampling. This is bagging. This is an important technique for assembling because random forest is just one algorithm that uses assembling. And as we said already, it's a parallel method of assembling. So in the end here, you can use your validation splits to evaluate the performance. And here again, it's written. So typically 1/3 of the original data set is not in the bootstrapped or bagged data set for a specific tree. The not used data is called out of bag data set because it's not in the bag. Random forest predicts for out of bag data sets and results are calculated, are used to calculate the out of bag error. So, I mean, bagging has this specific set of terms that you could use with out of bag data, out of bag error, but in the end, you could also call it validation error or validation set. Yeah. So it's the same thing, but different terms because we are now in the scenario of bagging. Yeah, how we predict with the tree, we already did that. It's pretty straightforward. So, and in this case, if we just use these example, the data point would actually be correctly classified. As I already said, if you want to emphasize weight of specific bags, you can use the validation error or the out of bag error if we want to stick to the bagging terms. Typically, you try to create all trees differently because you want to have a very diverse set of trees, and this is achieved through random sampling of features, bagging the data. Also, you can, but this is, I don't know how useful this really is, but you could also set specific helper parameters for a specific set of trees, so to make it even more diverse. But at some point, I'm kind of sure you won't boost the performance a lot more with even more diversity. Like there's a certain amount of diversity that you need for some link to work, but you can put it to an extreme. So you can test different number of trees, and in the end, you pick the best model. Yeah, and maybe to get back to your question again, a good rule of thumb, if you don't know how to set the hyperparameter for a number of features that you should start with to randomly sample, you can start with the square root. This is a good rule of thumb. I guess there are a few research papers on it that showed that you're not likely to get the very best performance, but at least this is a good rule of thumb to get a decent performance in the very beginning. So to summarize random forests, in the end, what you do is a decision tree is very simple, very easy to understand model. A random forest just gets complex by adding multiple of them. In the end, random forests are really competitive in terms of benchmarking. And as I said, until a year ago, they were on top. Like XGBoost or random forest were the best classifying algorithms for tabular data. By now, the shift goes to TAP-PFN, however you want to pronounce it. It was created in Freiburg, and they just built a startup around it. It's pretty easy, pretty interesting to see how deep learning slowly takes over the tabular data field. But yeah, random forests are still great. Yeah, they're lightweight and they have good performance. Okay, so let's go to the second ensembling method, and this is now boosting. We had bagging before, this is boosting, and again, be aware, boosting, I mean, the algorithm that we look on is AdaBoost. This is the specific algorithm, and they make use of boosting, and boosting is the general ensembling technique. There are multiple algorithms that use boosting, but we are learning it on the example of AdaBoost, just to be very clear here. So the interesting part is, in a random forest, the depth of the tree depends on how many features you randomly sample. Yeah, typically every feature is one decision node, and in AdaBoost they don't do that. They typically just have a stamp, so the smallest tree possible, and the depth of the tree is never higher than that. It's always just one root node, two leaf nodes. That's it. That's all you get in AdaBoost. Also, I mean, here it's now represented with the size of the stamps, but by definition, each stamp has a different weight. Or in boosting, we say the amount of say. Yeah, the weight and the amount of say again are basically the same things, but in terms of boosting, we say the amount of say. So they don't impact the prediction equally. In random forest, they do. When we just do majority voting, every tree has the exact same weight or amount of say in a random forest. Here it's different. And also, this is a sequential method. So the performance of one stamp actually influences the creation of the next stamp. And here you can't do it as in random forest, that you train like 64 trees at the same time, but you have to wait. You train one after another, and then you have a criterion when you stop, but this is how it goes. So the main concept is AdaBoost combines a lot of stamps to make the classification. Some stamps have more influence on the final decision than others. Stamps are created sequentially and take previous stamps into account. I already said that. Yeah, so this is the same data set again, but I removed H because it just makes it slightly more complex, and I just wanted to get rid of numbers. You have already seen how you build a tree based on numbers and thresholding and so on. So I just removed it because it makes it a bit more straightforward. So but apart from that, we have the same data set. So in the very beginning, instead of bagging the data set, here we apply, or we set a weight to each of the data points, and each data point gets the exact same weight. Yeah, so they are all equally important in the very beginning. And yeah, the way you apply these weights is pretty straightforward. You divide by the number of samples, and then you just insert a column, you add the weight, and there you go. And then we build the first tree. And we do this again with the GINI index or GINI impurity. We have already talked about this a lot. How to build these trees, or how to calculate the GINI impurity. And here it's again, now we focus on the first feature. And for AdaBoost, you always focus on all features. So in the very beginning, if you want, since a tree is just one node and two leaf nodes, so one root, two leaf nodes, you have to decide on which feature you want to focus on. And again, the goal is to start with the feature that separates the data in best possible way. So you now have to calculate the GINI index for all features. And is it clear to anyone how we come up with this numbers and how to calculate the GINI index? I mean, I can explain it again, but I can also save some time and don't do it. Okay, yeah, so we create these first trees to calculate the GINI impurity. We have done this before, and the GINI impurity for those three trees is the following. Swollen has 0.28, pain 0.381, and movement possible 0.214. So which of those features are we taking? What? Oh, yeah. Movement possible, right? Because it has the lowest GINI impurity, so it's best suited to split the data apart. So none of them is 100% pure, so you have to start somewhere. We start with movement possible, and that's the main reason why I deleted the H column, because it just takes the longest to compute. But it should be pretty clear by now on how we end up with these numbers for each specific feature. So in the end, we decide on movement possible. And this is how we continue. Now we built this tree already, and we used it to calculate the GINI impurity. But now we need to calculate the amount of say, because movement possible is basically the first stamp that we add to AdaBoost. And we have to come up with the weight that it gets to decide on how to continue building these trees. So the formula to calculate the amount of say is the following. The only thing that really needs to be explained is how to get to the total error. And it's actually pretty straightforward. The data point 6 is the only one that is misclassified. And the way we do it is when we have the decision movement possible, the left branch is yes, the right branch is no. And then we basically just see if the movement possible is yes, how many times our label column is also yes. And if we say movement possible is no, how often is the label column for these data points that have no movement possible also no? And there's just one data point that sticks out. So despite there is no movement possible, it's a knee injury. Yeah. So this is the only one that doesn't map. Yeah. So you map yes to yes, no to no. And there's one example, and this would have been misclassified, because if you answer the movement possible question with no, the final answer is not no. And does this make sense? Is this clear? So there's one data point that is misclassified. And if we look at the data, this is the one. So movement possible is no, but our label says it's a knee injury. So this is the data point that we misclassified. Is it clear? Now is your time to ask. I'm happy to answer all your questions. Can you speak? I have to wear this stupid AirPods, so I can't hear you that properly. I mean, this is just what the data says. I mean, yeah. I mean, you would guess that if no movement is possible, I mean, how the data points look like, we don't make the data points. We just use what is in there. I mean, to be honest, I created the data. And I wanted to do it fast, so I just pasted in random yes and no values. So there is no sense to it. It's not medical data. It's brain dump. Yeah. So the data necessarily does not need to make sense. Okay. Okay. Let's get back to the total error. So and then we take the weight of the total error. So if we have 2 data points, the total error is 2 out of 7. If we have 3 data points that are misclassified, it's 3 out of 7. Now we have 1 data point, so it's 1 out of 7. Then we paste this in and we get the amount of say. And this is the number. So this is basically the weight that this stamp, the first tree of AdaBoost, gets. And I very briefly plotted how this amount of say can look like. So depending on the total error, the amount of say can also be negative. Like this scale, it's somewhat tiny, so it goes from 3 to -3. So if you misclassified all data points, which is very unlikely, but in theory possible, you would have a negative amount of say. So you have a negative weight. And if your total error is close to 0, it's around 3, your amount of say. So it's a positive weight. It's important to understand that the amount of say or the weighting of the tree is not necessarily always positive. And the impact it has, we come to that later. You just have to store now can be negative. And our value is 0.89, so our amount of say is somewhat here. Just to visualize it, that you can see how this formula impacts the weighting. So let's come to the almost last step of AdaBoost. We need to update the weights. So for all the positive weights for all the weights that you misclassified, this is your formula. Yeah. So here it's 1 divided by 7 times e to the power of 0 point and then the amount of say. And this is the new weight that it gets. And for all the ones that you have correctly classified, it's e minus the amount of say. E to the power of minus the amount of say. And this is now true for all the other weights. And these specific numbers, they don't have to make sense. It's just the way to calculate the new weights. Yeah. So the author of AdaBoost thought that this is a very nice and easy formula, and therefore he ended up. There is no specific meaning. Like, I can't tell you if it's 0.0583 that it has a specific context. It's just the value. The higher the value is, the more importance the data point has. Yeah. So in our case, all correctly classified data points, they get a low weight, so low importance. And the misclassified data point has a higher weight, so higher importance. What would you say? Why does the one data point that we misclassified needs to get a higher weight compared to all correctly classified data points? Yeah, yeah. I would argue it's not that dependent whether it's a majority class or not, but we are in assembling. So we want to improve performance through multiple models. So if now we know that most of the data points in the data set are already correctly classified. So if we want to get better, we need to get better in classifying the data points that we couldn't predict correctly in first place. So if we want to improve the performance of the next tree, we actually need to get better in predicting this scenario where we misclassified it. Yeah. So this is the sequential aspect of it. Now we built the first stamp. We calculated the weight or the amount of say for the stamp. Yeah, we have all done it. And now we need to decide how this impacts the creation of the next tree in AdaBoost. So it's a sequential method. And the next tree should always focus on the data points that the previous tree misclassified. So that all the data points that they misclassified have a lot higher weight. And then over time, what happens is you focus more and more on all the data points that all the past trees couldn't classify correctly. And with this, in an ideal case, the longer you learn, the better your performance get. Yeah. And by the longer you learn, I mean, the more trees you create, the better the performance gets. That's the core idea of AdaBoost. So in our case, once you calculated the weights, you normalize them so that the sum of all weights equals 1. Yeah. So, and after we normalize these weights, we sample them again. Yeah. And can you remember when we inserted these red thresholds in the age feature of random forest? Like, these were all possible thresholds that we have. Like, and now what you do to really apply the weight to this one data point is you sample the data out of your data points based on the weights. So you typically choose or pick a random number between 0 and 1. And now you have to think of all these data points that are in between the values. Like the first threshold is 0, then you take 0.833, This is the next threshold. Then you add the next number to it. So you end up with 0.1666 and you end up with, so you have all the intermediate steps when you sum it up. And since we normalized it, the overall sum is 1. And the only reason why we do it is because then we can sample it somewhat easily. So if we pick a random number, and this is, for example, 0.55, we just have to look where, based on the threshold, which data point we are actually picking. So this one is between 0.4999 and 1. So the data point that we would sample based on this random number is the last one. And since the range of the last data point is the highest, if we assume we have a normal distribution while random sampling, we will most definitely sample this one data point that has the highest weight most often. So if we have now the new data set, this is data point 6, and 6 appears 1, 2, 3 times. So almost half of the data set is now this data point that we misclassified. So the next tree, if it makes the same error again, it will first of all get a lot lower amount of say, yeah, because it didn't make it better. And second of all, it would even more focus on the misclassified data points. And if you do this a few times, you basically end up only with the data points left that you misclassified previously. And this is the sequential part of it. So once you have your new data set that is created based on the previous tree, you start from the very beginning. And it's over and over again. It's basically a loop. So and then you end up with this series of trees that you have. And now let's get back to our final prediction or classification. So these trees always, in our scenario, I don't insert the data point, but these trees that you created, they say he has a knee injury, and these trees say he doesn't have a knee injury. As you can see, more trees actually say that he doesn't have a knee injury. So if we would do majority voting as in random forest, we would say he doesn't have any injury. But in AdaBoost, we always have the amount of say or the weight of the tree. And then you basically add the weights up. You just sum them. And this is the interesting part of why these amount of says can be negative. Because in the end, if you have, if your tree says it is a knee injury, but the total error was close to 1, so it misclassified all data points. Yeah, if you sum the negative weight up, it will actually reduce the amount of say of the trees that say it has a knee injury. So this way, we know that it's most likely misclassifying the data point. So therefore, we subtract weight from it. Therefore, it can be negative. And in the end, we just sum it up. And even though these are more trees, these trees have a higher amount of say. So our final prediction is not based on majority voting, but our final prediction is actually based on the amount of say of the trees. And in this scenario, we would say it's a knee injury. So main concept recap: AdaBoost combines a lot of stems to make the classification. Some stems have more influence on the final decision than others. Stems are created sequentially and take previous stems into account. Is this clear? As I said, it's very, yeah. Yeah, I mean, you sample multiple times. Yeah, the length of the new sample data set has the same length as the original data set. Yeah, and if you assume that by random sample you have an equal distribution, the chance that it will always sample these tiny numbers is relatively small. So it's just a matter of statistics. Like by chance, you will sample these data points more often. Yeah, like most likely the points that are missing in the data set are the points that you classified correctly. Yeah. So, and you don't need to train again on the data points that you already know how to classify. You need to talk a little. No, it's not completely random because you have the weights. Yeah, it's a random number, but the random number needs to be in these intervals. So for example, everything that you sample that is 0.5 or higher will sample this data point. Yeah. So by chance, 50% of your sample data will be the last data point. I mean, let's go through it. You give me a random number between 0 and 1. 0.2. So 0.2 would be this data point here. Data point 2. So you select it, you put it in the table. Give me the next random number. Yeah. For every entry you sample a new random. Okay, perfect. Yeah. If a tree has a high error rate, why? Yeah, we do that by the negative amount of weight. So if we are at this step and we have the amount of say, and we know that it misclassifies all data points, it will get a negative amount of say of -3. Yeah. So, and if we take the sum of all of these data points, it will reduce the sum by 3. And this actually will boost the other trees that correctly that predict the other outcome. It's not clear. So here you have the tree, and it has amount of say of 0.8957. And let's assume this one has an amount of say of -3. Yeah. So then the total sum would be negative here. Yeah. And by making this one negative, actually it will boost the opposite. Because this doesn't get subtracted anything. So therefore we are using it in the opposite way implicitly by the negative amount of say. Yeah. Is it a bit clear? Yeah. Yeah. Oh, I just didn't paste a data point in there. But what you do is if you take any data point of the table, of your test set, for example, you will just behave like any other decision tree. Yeah. Yeah, the amount of say is fixed. No, because for one data point, this tree could say has any injury, and for another data point, it could say doesn't have any injury. So the sorting changes, and therefore, yeah. Okay. So then let's recap everything that we learned so far. We are back to our one of the very first slides. We now covered a sequential method as in AdaBoost, and we covered a parallel method as in random forest. Both of these use assembling to get the score better. By now you should, I hopefully should know what the differences are and how in AdaBoost one tree impacts the creation of the next tree, and in random forest they don't impact each other at all. Again, it is very, very important to know that this is now one begging example again. And when I gave this lecture the first time, to some students, it was not clear that you could use other classifiers than trees. So if we get back to this visualization, here the models can be anything, any classifier. Yeah. So typically assembling is used in based on trees. Now it's a good question. Why would you think are we taking trees that often, decision trees that often to ensemble? What is the benefit of a tree? Faster? Who said it? Okay. Yeah, yeah, yeah. Then? Yeah, yeah, as well. I, I guess in this case I wouldn't fully agree. Like the aggregation of the model is always the same. But to get to the output of the model, that's the difference. So first of all, predicting with a tree is fast. Yeah. And the overhead explodes the more complex models you insert. So if you, in this case, have 4 different deep neural networks, yeah, training them would take forever. And then in this case, you would need to train 4 of them and not just 1 or 2. And typically ensembles, they work on diverse data. So maybe you would have 8 of those deep learning models. And at some point, it just doesn't, it's not feasible anymore. Many of those deep learning models, they are fast in prediction. Like a forward pass, you haven't had neural networks yet. You will come to that. But a forward pass, a prediction is just a forward pass in a neural network. That's fast. And once you have all the outputs of all the models, aggregating them by majority voting is also really fast. Yeah. So just taking a sum of all the outputs it's not the main concern. The main concern is basically training time. And I work in the field of recommender systems. Professor Bill also offers a recommender systems lecture. Does any one of you attend it currently? Okay, let's ignore most parts about recommender systems, but what they're used for. You make predictions in an online scenario. For example, if you visit Netflix, all of those rows that are shown to you, every row is generated by a machine learning model. And also the sorting of those rows is done by a machine learning model. And you really don't want to wait 20 minutes until your front page shows up, right? So actually being fast is a huge advantage in most fields. I mean, maybe in the medical domain where you just want to focus on a very precise model and it's not too important to wait 10 minutes. There maybe assembling could have a higher benefit. But if you want to use assembling in live systems and you want to have the predictions straight away, then assembling can introduce another overhead. But yeah, here it was just important to know that you can include multiple models. So in this case, you can use KNN, linear regression, SVM, and this is also interesting, also random forest. So you can ensemble random forests. So it's basically 2-stage ensembling. So within the model, you ensemble, and then you ensemble the model. It can all work. I just want to make this very clear. And then in the end, how you aggregate it, it can differ. You can do majority voting, weighting, Bayesian model averaging is another technique. But this is an introduction course, so we don't need to get too much into detail. And we already partly covered this. So typically, if you have a pipeline, you have your training data, then you train classifiers. Then you typically select classifiers based on validation performance, and then you use these to ensemble them. Like typically, you don't use every model that you have in an ensemble, but just very diverse ones, or very good ones, or ones that are trained on different data and so on. So this is a whole research field, basically, just to figure out what models to pick. And then you put this into an aggregation function. Sounds fancy, but most of the time it's just majority voting. And then you have your decision. And then this is how you can see ensembling in the whole pipeline of machine learning. Yeah, so concepts can be applied to all kind of algorithms. So ensembles describe a way to combine models to improve a score. Random forest and AdaBoost are examples where assembling is used out of the box by definition, but you can also apply these techniques to other models, whatever. Ensembling is not only used on decision trees, very important. Ensembling can be used for any learning algorithm. Ensembling can be seen as an additional way to improve the performance. And that's it. Okay, if you have any more questions, you can always ask now or come down to me later on. I will most likely won't give another lecture this semester. So best of luck in your exams. Anyway, yeah, it was a pleasure.